Our next topic is the Bernoulli sequence. Often we'll have a case where the outcomes are discrete, what we call trials. By that, an example of it would be the previous examples we did in Chapter 2 and earlier in Chapter 3 of the bulldozer. It's either operational or non-operational. So an evaluation would be for the single bulldozer, is it operational or is it non-operational? That's what we would call a trial. Perhaps a load from a vehicle, when it's measured, is above a limit or it's not. That would be a single trial, one evaluation of a vehicle at some limit. Your textbook also gives a couple of other ones, a series of piles driven into a soil stratum. Each pile may or may not encounter boulders or hard rock, and the examples are countless. But each of these examples is a single trial where the outcome is either one way or the other. So to define the Bernoulli sequence, we have three assumptions. The first one is listed here at the bottom of this slide, that each trial has only two possibilities of an event. It can be the occurrence of the event or the non-occurrence of the event. That's it. One of two options. Flip a coin, it's either heads or tails, so the occurrence of heads or the non-occurrence of heads. The second is that the probability of occurrence in each trial is constant. So we have each of the discrete trials has a single probability of an occurrence. This is constant for all of the trials. If you repeat the trials n times, the probability associated with each of the trials is the same. Remember the bulldozer example? The bulldozers had an equal probability, a 50% chance of either being operational or non-operational after 6 months. That applies to each of the bulldozers in that example. There were three. So each trial would be associated with one of the bulldozers and evaluated at 6 months. Is it operational or is it non-operational? So the occurrence or the non-occurrence, in this case, of operational. And finally, the trials are statistically independent. So the first bulldozer being operational, non-operational, has no impact on the second bulldozer being operational or non-operational, and those two have no impact on the third bulldozer being operational or non-operational. They're statistically independent. The outcomes are not related to each other and influence each other, as we talked about statistical independence before. So really what we have is this kind of illustration at the bottom of the slide here. If we have discrete trials, trial 1, trial 2, 3, all the way, say, trial n, there are exactly two outcomes. It can be the non-occurrence or the occurrence of some event that we're interested in. For each of them, they are statistically independent. They're each treated as separate trials. They have no impact on the outcome of any other in the trial. When we take all of these together, what we have is what we call a Bernoulli sequence. The Bernoulli sequence we want to assign a probability to. And to do that, we use the binomial distribution. A couple of definitions. X is going to be the random number of occurrences of an event among n trials. So for the bulldozers, we may say that the number of occurrences of an event among n trials, we had, let's say, 3 trials, because after 6 months we evaluated the 3 bulldozers, and each bulldozer evaluation of being operational or non-operational is a single trial. So we had 3 trials, and X would be the random variable associated with how many occurrences, or operational in this case, there are. P is the probability of the occurrence of the event in each trial. And 1 minus P is the complement of that, which is the probability of the non-occurrence. With these definitions, we can define the probability that our random variable x takes on some value x among n trials is a binomial distribution with PMF for probability mass function because we are discrete. We're not continuous in this case. The first couple of distributions that we looked at were continuous, the Gaussian and the log normal, but now this is a discrete probability, so it's a probability mass function. And the CDF, the top equation here is the PMF. The probability that x takes on a value x is going to be equal to, this is what we call a binomial coefficient, times the probability for each trial having an occurrence raised to the x times 1 minus p, this is the probability of the non-occurrence then, raised to n minus x, where x can take on discrete values of 0, 1, 2, dot, 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 all the way up to n occurrences. This binomial coefficient is defined here. This is the textbook usage of it, and this is pretty consistent along different mathematical disciplines for the combination coefficient as well. This is defined here. The binomial coefficient is n factorial over x factorial times n minus x factorial. So this is the PMF of our binomial distribution. The CDF is simply the sum of these over all the occurrences. So we sum up the discrete probabilities associated with the x number of occurrences out of n number of trials, from 0 all the way up to n number of trials. So it's simply the PMF for each of the discrete occurrences over n number of trials. Our textbook has table A.2, and it's a little confusing to navigate at first, but let's take a look at it here. I've reproduced just the first portion of the table on this slide. This is the CDF, where n is the number of trials that we will have, and x is the number of occurrences that we're looking at. And unfortunately, in the definition here, the CDF uses k, and then the text uses x here. Really, this should be k to be consistent with the notation that they're using. And this should be n. The way that we read this is the top is the number of trials, the top of this first row here. This second heading is x is going to be equal to the number of occurrences. So we can have 2 trials and we can have 0 or 1 occurrences. Notice we wouldn't have 2 occurrences because that would simply be guaranteed. We have 3, we can have 0, 1, or 2. For 4 trials, we can have 1, 2, 0, 1, 2, or 3, and so on throughout the other tables as well. And then the final on the left here are the probabilities that are associated, P, with each of the trials. So if the probability of the occurrence is 20%, then what we would do is follow this row along until we got to what we were looking for, where we have the number of trials and the number of occurrences that we're associated with would be, for example, let's say for 1 we were interested in at 20% for each of the probabilities, then we would use this as our solution of the CDF. It's also easy to do on a handheld calculator or in MATLAB or in Excel because this is a discrete function and there's the solution to each of the equations depending upon the number of trials and the number of outcomes. The only thing you need to calculate is the binomial coefficient, and any handheld calculator can do this. The factorial, you can just crank it out, given by the definition of the factorial. I have an HP calculator that I use. I know there's a combination function in there that does this directly. If you don't have access to that, you can use MATLAB or Excel, which I'll show you in a second, or Pascal's triangle, which I think is a little off topic, but it's a neat application of many of Pascal's triangle. So one way to calculate what the binomial coefficient is, we can use what's called Pascal's triangle. This is used. This is one of its uses among several others that the famous mathematician Pascal devised. And to use the Pascal's triangle, we have to remember that it is a zero-based counting system. So the top of Pascal's triangle, we're going to call row 0. So let's put 0 out here. And the second row of Pascal's triangle is row 1. Third is row 2, and so on. And you might notice that the way this is set up is we start with 1 at the top. We have 1 on the sides for this row designated as row 1. And then what we do is we add, for all the interior nodes, the previous row. So 1 and 1 make 2, so the next row is going to be, we're going to transfer 1 down, and then we're going to add an element based on the sum of these two nodes for row designated as 2, row designated as 3, which is the fourth row down. We add the nodes again, so we transfer 1 down on the sides, and then we add these two interiors from 1 and 2 to make 3, 2 and 1 to make 3, and then again 1. So this continues all the way down to infinity, and what we have is a kind of a neat way to figure out what is the binomial coefficient. And the way that we do that is we use the row numbering system as the number of trials. So what we may want to find out is, let's say we want to find out the binomial coefficient for n trials equal to 10, and let's say k equal to 5. So the coefficient, we would go using Pascal's triangle, we would take 10, and this designates what the row is. So we would go down and we'd see that we'd be all the way down here. This is row 10. And you may notice that actually if you follow this line down, this really designates our row number in our zero-based counting. So row 10, and then we'd want the element k equal 5. We do count in, again at zero-based, 5 spaces to the 5th entry, which, the number 5, which is zero-based, so we have to start with 0, 1, 2, 3, 4, and then we end up here 5. So this number is the binomial coefficient for 10 trials, 5 at a time. We can also find the binomial coefficient using MATLAB. There's a built-in function, n choose k. And n choose k, if you're not familiar with MATLAB, I suggest you use this more help. And we see that it's binomial coefficient, and there's a couple of different calling methods that we can use. But for this case, we wanted to say, again, let's do 10 taken 5 times for our binomial coefficient, and we see the answer is indeed 252. We can use Excel to find the binomial coefficient. This is nothing more than the combination. So the calling function in Excel is combin, and number, let's say, keeping consistent 10, and number chosen is 5, and we see we get 252. At this point, I would direct you to the video of example 3.14, which goes over an example of, in your textbook, of the binomial distribution for a machine life. And it's a pretty good illustration of how you use this distribution.